I know what you have been doing last night.
Not these ones, the other
Okay,
ones.
I know what your colleagues have been doing. Some of them arrived quite late, but
So I will send an email to everyone to remind that participation to the lectures are compulsory. I believe that almost all of you receive some money from your institute, the IFUSP, etc. So, no, no, yeah, yeah. Exactly, this is what I explained.
you can pick up the certificates, tier it, give the first half at the beginning, and the second half you keep on in hand. They'll be delivering only on the last talk. Okay. Uh, I fear that I have scared you with all the integrations and transformations from one side to the other, from the vector into the matrix, into the representation, into the characteristic function. I promise that today won't be so dramatic in calculations. We are going to to deal with the experiment. We are going to measure the field. So what's the idea now? The nice part, the part that I love in quantum optics, is that you can do really quantum mechanics going beyond all the difficulties that you have with manipulation of matter, being it solid state or even atoms. But when you deal with optics, there's some curiosity that comes out. Okay, electromagnetic field, you can think of all the radio waves, everything that goes when you deal with electronics. When you go up to the microwave region, you're always using antennas. You're never using the measurement of the power, or it's pretty rare to use that. Most of the time, you just convert the inciting electric field into a current, and then you process the information of the current associated to the field. So that's what we call telecom. That's how the voice here is going to radio waves, to the amplifier, and processing it and sending to the loudspeakers. You record, amplify, analyze. You have electronics for that. And there's the nice demonstration of that 3K background, in fact 2.7, that was recorded by Penzias and Wilson. They had a microwave antenna. They cleaned up all the noise. They began with the desperate hypothesis that somehow the goo from the pigeons that were inside the antenna were affecting the measurement. They scrubbed out all the dirt out of it and kept with that background noise that comes out. That's really the background noise from the cosmos at a temperature of 3 Kelvin. It's a black body radiation that you fit the curve. This is an old one, so it's using the COBE satellite information. The latest one that's had from the Planck and WMAP that gives even a better resolution and fits nicely the black body radiation. But that's all using the measurement of the field. What's the problem of doing quantum optics in this range? Okay, even these 3K cosmic backgrounds comes as a cost. It gives you a strong photon density. So it comes hard for you to clean out the background noise in this situation. A Roche experiment at in the range of 9 gigahertz, he put that in a huge cryostat that's working on liquid helium, and then it needs to make another step to get it down to all the techniques that have for evaporation of helium to get it to sub-Kelvin temperature. to get rid of this background noise. So every measurement needs to account for the thermal background. So on the other hand, if you go to the optic domain, you don't measure directly the electromagnetic field. In fact, you take the average over the Poynting vector, so the flux of energy, and then you use the photoelectric effect, the second signature of the quantumness of the world after the black body radiation from Planck was the the photoelectric effect, the ejection of photons by a metal where inside light, and then you produce from the absorption of one photon the production of one electron. So this effect will convert photons into electrons. And that's the tool that we'll be using, either looking with avalanche photodetectors or photomultipliers. They will take an exciting photon, produce one electron that will be accelerated, and on this process of acceleration, they can transfer this energy of this accelerated electron into the substrate, either a bulk or the bulk of a semiconductor, in the case of APDs, or as it was before, this energy would be used to collide with a plate and eject other electrons, so that will multiply the number of electrons in a completely random way. So when you have a click, that click is quite big, it's a huge bunch of electrons that tells that at least one photon was detected. It could be two, could be three, could be more. So you have a strong pulse coming out, and most of the times you'll be dealing with the discrete variable domain. Or you can have a strong flux that will produce a noticeable current of the order of nano, micro, milliamperes. And that's something that can easily convert into a voltage and amplify afterwards. So it's very nice, because when you go into the EV domain, so 1 electron volt is 1.24 microns, the wavelengths that you're dealing with. So that's the near infrared. That's a little bit longer than the wavelength of a neodymium YAG laser. Who has here played with a neodymium YAG laser? Raise your hands, okay. Telecom lasers, other lasers, that not this laser, not a laser like this, okay? But okay, even a laser like this, that's 600 nanometers, so that's 2 eV. So in this range, it's nice because for the photons are energetic enough, every photon counts, okay? And the effect of this background will be basically the same if you done that in liquid helium. Remember, if you go to the Boltzmann relation, things that will be evolving with E, h bar omega, kT. kT at room temperature will be something like 25 milli-electron volts. So when you put here EV, you see that the density of photons goes down dramatically. If that's room temperature, that's 300 Kelvin, so you can really play at room temperature with no problem. In some experiments, when you go to continuous light, you even work with lights on, because you can just filter out the light coming from your lamps and work with your lights on. When you go to photon counting, you'd better turn off the lights, not to damage your photo detectors. But this nice point is that overall, at the end of the day, we have cheap photo detectors. This one is quite efficient, but they're not going to put that on your beam, in your beam path. I strongly don't recommend you. But they can be used to see the scattered light and check out the alignment on the tabletop. CCDs they're basically everywhere. Now everybody has a CCD camera on your pocket, or the variations of CCDs, the new generations of CMOS. And at the end, you want to work with photodiodes like this. So remember, when we say photo detection, we can have two different kinds of photo detections. Either you're counting photons, photomultipliers, you get one photon, they give a click. They're dominant up to the 80s. Now in the 90s, they became replaced by avalanche photodiodes. They're really nice to work. And nice part, besides they don't break, you don't need to cool them. Okay, you need to cool them, but it's not so dramatic. You have those Peltier elements. You see those wine coolers that you have in a house where they want to keep the wine at 10 degrees, so etc. You know what that stuff? Okay, that work using those Peltier elements. Just pass a current through it, it produces a difference in temperature, so it can cool down some small volume of a material using those elements. And for cooling an avalanche photodiode or a CCD camera, they work pretty well. You can cool it down to 0 degrees Celsius or a little bit below that. So these two, these surpassed this one with the advantage that they're much more efficient. You can reach 70, these would be typically, the best would be around 20 to 30% quantum efficiency. So the best one would be out of 3 photons, it would detect 1. The other would be lost due to reflections on the surface. Avalanche photodiodes can get to 70% or more. And now that's nice. You can do even better if you take a nanowire of superconductor, and when the photon incides on that, it absorbs the photon, heat up, and get out of the superconducting regime. And then suddenly you have the break of this superconducting regime, and then you see a voltage appearing over the tips of this wire. So that's really nice, and can be used to make number resolving photodetectors. You can count how many photons arrived. For that, it also needs to be quite efficient. You can get more than 90% efficiency here, so we can have those guys measuring the number of arriving photons. Up to 12, the more photons you have, the fancier and more expensive they will be. They'll be working on liquid helium with evaporative cooling, with helium liquefator to get temperature down to sub-Kelvin regime. Or, life's much easier if you go to continuous outputs. So work with PIN photodiodes, and with some electronics on top of that. Well, those that are familiar with electronics, they recognize here just an operational amplifier, or a feedback resistor, and the inverse polarized diode here. Light inside, produce a current, it's amplified, you have a voltage in the output. And that's something that you process easily. So we can easily measure the photon flux, the field intensity. And for the rest of the seminar, I'll be dealing with the continuous variables regime. We will get back to experiments where we'll be looking at photon clicks. But then I warn you that we will be working on the discrete regime. For the continuous variables regime, you'll be measuring the optical power. You're making the integration of the transverse area of this incoming flux of photons. So be having something that will be proportional to your number operator converted into a photocurrent. So that's the observable, and that's how it works. Basically, you have a photodiode, you have the N and P doped regions, and when you have an inciding photon, it will produce a separation, a split in this intrinsic region. So here you have a non-doped region, where the inciding photon will produce a pair of electron and a hole. The hole will migrate to the P region, the electron will migrate to the N region, and then that will produce a current here, a current flow in this system. That's basically how a photocell works. The incident light will produce a difference of potential here on these extremities and on these extremes, on the terminals, and then you can use either for energy or here for measuring the number of photons that have inside it. And now, hello from the audience.
This is a thing that I always try to understand. So you can define the quantity of photons in terms of H bar, something like that?
Exactly.
So you count how H bar are you measuring in? You convert sure from current to voltage, or for energy, and you count how many energy do you have in terms of H bar, and from this you know how much photons are you detected.
Exactly. The accountability here is that you have some proportionality between the current and the proportional to the power inside on the detector. This power will be a certain number, n, of photons times H bar omega, the energy, involving a certain time or a certain energy at a certain rate.
What is K?
And
What is K? This K. K kappa?
K is a proportionality constant.
Okay.
Okay? And current will be a certain number of electrons times electrical charge with time. Okay, that will be related with K.
Mm-hmm.
You feel that I'm missing something, and there's something missing here. It will be the number of electrons, and in fact, the number of electrons will be corresponding to the number of photons times a certain quantum efficiency. Okay? So that's the point. You have here this constant that will depend also on the efficiency of your detection. So
okay, so you need to calibrate it before to find
exactly.
the data.
So it's always recommended that you calibrate your detector and check out what's the quantum efficiency. And that's the nice part. You can build those guys with up to, off the shelf, you can get 90-something% quantum efficiency. With paying a little bit more, okay, you can get 95. If you pay a lot more, like the folks at the LIGO interferometer, you can get 99. So you're losing one photon in 100. At that point, you're not so worried about your detector, but with the optics on your tabletop.
And Serge Roche.
Huh?
That's per
Serge
meter.
Roche is doing with microwaves.
Ah, yeah.
So he's not worried about that. He's measuring the field, but his detectors are quite different. Are atoms that are probing the field inside the cavity. So what's detecting light, Serge Roche's group, are the atoms. So that's the nice part of the Nobel Prize of that year. Serge Roche got the prize for manipulating the quantum state of light with atoms. David Wineland got the prize for manipulating the quantum state of atoms with light.
I have a question also with this. That delta T here then is related with the integration time of my detector, or not
No,
necessarily?
just the rate, and you see
Okay.
that you can just. It's not on top of this for the moment. We're taking an average over a certain time. What's nice here is that if you get back here, then this NE will be eta NP cut it, and now this proportionality constant will be efficiency, electric charge, h bar, lambda, times, whoops, C times lambda, or eta lambda divided by 1.24 micrometers. So when you measure the sensibility and see here that they're relating milliamps with milliwatts, you can, from this constant, relate it with your quantum efficiency, considering always what's the wavelength you're working with. Okay? So that's the typical calculation that I always ask people in the lab to check out. What's your quantum efficiency? And that's fundamental for you to know, okay, which detector are you picking up? Other questions?
Is the guy that produced the device that give you they give you the K number, or is you guys from the lab that does it?
They give you a curve of this K. There'll be something that begins here, say 400 nanometers. Here will be the wavelength, which you get up, go like this, and then we break down. Okay? What you have here? Here you have the glass window of your detector. So in the, okay, probably 400 will be more likely here. Above this region, the glass window will be absorbing. And here, below a certain point, what you're having is the limit of the band gap of your detector. So the energy of the photon will be below the energy of the band gap. So we won't be able to promote the electron to the conduction band and leaving a hole behind him. So you won't be able to excite it, and then you can just take the curve from this relation here with eta equals to 1, that's some linear. And from here, you can take what's your quantum efficiency. Okay, that's what the salesman tells you, and that's what you go in the lab and measure. So you'd better check. In a batch of detectors, eventually you can have one better than other. And then you have to look after whether you're working with silicon or gallium arsenide to see what's the range that you're working with. Or indium gallium arsenide, or all the kind of spices that you can play with these combinations, with those 3-5 combinations to get your photo detector working on that specific range of energy.
Professor, may I ask you a question here?
Yeah, sure.
Do you have a specific source that you use to do benchmarking of these devices?
No, we can take the laser that you're using on your tabletop, and then you need to calibrate towards the incident power. With that, you often have a calibrated detector that you buy from a company, say Tor Labs, Coherent, not to make advertising of any one of them, or then give you a detector. Is identity traceable back to some NIST bolometer that will be that's a certified measure for measuring the efficiency, for measuring the power, and so all of them have a specific calibration. So you trust them; they're pretty reliable in the order of some few percent.
Thank you.
Okay. So you take that reference and you compare your detector with that reference, and then you can measure this, the power, and the current is pretty immediate. Right? Okay, we got the current, so we got the power. Now remember that you're always considering often the a given mode of the field, counting the photon number in that mode, in principle, is a discrete spectra, but comes to some tricky points. Okay, so if you have a single electron coming out here, at that point, you won't be able to distinguish this single electron coming out here from an electron from the leakage that you have in a regular diode. So one electron will not do any great effect here. Moreover, all of your electronics, they suffer from Johnson-Nyquist noise. That's basically the problem that you have a resistor. So you can see it as a box with a gas inside. The electrons are your gas. So you have a fluctuation of collisions with one side and the other in the case of a gas. So you have a statistical fluctuation of your voltage across a resistor. If you heat it up, the variance increases. The mean remains 0, but there's a fluctuation here, and you can measure that in the lab. That's something that you have to fight as well. Okay, that's the nice part when you deal with a huge flux of electrons. So you're in the continuous regime. So the discretization of the spectra is no longer noticeable. You'll be seeing it as a continuous variable. Okay? So those are our tools for measurements. Let's see what we are measuring, getting back to the problem of coherence. And I would like to bring this article here. It's not so much called the attention, but that's the basics of, you see that the book from Mandel and Wolf is called Coherence and Quantum Optics. Because coherence lies on the heart of all the experiments that you deal in the optical domain, playing quantically in the optical domain. So what is placed here, it has a source. I can change it either two pinholes, can change the size of those pinholes, or a single pinhole and it changes the size of it. The light emitted from this transverse pinhole is incoherent. So it has the interferometer here, it collimates. Sorry, I'm messing up. This source is really a pinhole, so it's a point source. So lights come out coherently from here and distributed here on this plane. And here, the aperture A can be a pinhole that can change, in fact, an iris that can change. It's not, in fact, it was not using an iris. We were using a set of slides with different diameters, or pairs of holes with different diameters, so you could change the distance and the aperture. And then he would project here into a film and register the interference fringe coming out. So when he was using a pair of holes here, you could see the usual interference fringe with a good contrast, but while he would be opening up the aperture from 0.6 to 0.8 to 1 centimeter, it would become blurred. You have a reduction on the contrast of your interference. This contrast in interference is related to the coherence of your problem. And at a certain point, it basically can cancel out, then have a revival. If you go to the calculations, is the modulus of a cardinal sign, or in fact here is more Bessel function normalized by the aperture A. So you have this sort of oscillatory behavior here. So the visibility for a source of partially coherent light will goes up, will goes down as you open it up. Because you have interference of different parts of your source, and they don't have a phase relation. So that's destroying your interference. That's important. That's in fact a very important tool, because you can use that to see the change and associate that with a distance source. So that's the idea behind the Michelson stellar interferometer. So when you take the light coming from a star, pass through 2 mirrors with a long baseline, and make the interference of them, you can see different parts of light coming from different parts of the star, and the resolution is given by the size of this baseline. So playing with the contrasts here, changing the separation. So here is something that can play either with a fixed aperture and aperture separation was held constant, and was changing the size of the source. Sorry, here it was changing the separation between the spots. What you have here is an information of the light coming from a star with the contribution with very tiny angles. The resolution is increased here because you need a difference of the order of a wavelength. The angle can be pretty small if the separation between the mirrors is pretty high. That's very nice. It works well. You can see a nearby star like Sirius. But on the other hand, it can't go much longer, much more distant than that, because then with a baseline of some tens of meters, the information is blurred, not due to the resolution of your star, but to the disturbation that you have on the beam path. So light here, you have all the winds and fluctuations and thermal fluctuations that will affect the coherence, and you have a destruction of the coherence coming from atmospheric effects. Okay, it works well, but with the atmosphere, it can be crappy up to a certain limit. It's bounded by the atmosphere. On the other hand, Humphrey, Brown, and Twiss proposed a new type of stellar interferometer, taking the light of a distant star and comparing the fluctuations, not in the field, but in the amplitude. And now comes the nice part. When you take the amplitude of the incoming light, you're throwing away the information of the phase. So you're taking just the photon flux and checking out the fluctuations that will be translating this correlation now into intensity correlations, not amplitude correlations. And with that, basically had 2 detectors, photomultipliers, on the focus of 2 parabolic mirrors, pointing to a star, Sirius, that was well characterized, and make a different delay on each arm, and make the multiplication here, and counting the coincidences or multiplying the intensities and taking this correlation on intensities. Okay, this was done in November of 56, but before going to a baseline here, where they have a baseline of some 10 meters, and could see the degradation of the normalized correlation here, they did it in the lab with a source. In January 56, they announced the result. So they had a pair, that's the idea of what they have, the radio interferometer, the one in the optical table, and how to emulate that. They take a source, light from a mercury arc, they filter out for a single wavelength, send through a beam splitter. This half-silvered mirror gives half of the light coming this way, half of the light coming this way, and then they shift one of the photomultipliers, changing the time it takes to arrive here, and check out the correlation rate when they shift these 2. Okay, you have an intensity fluctuation, you divide it by 2, compare the fluctuations in intensity, and you see when you match the time of flight between this and this, you have perfect correlation. When you put a delay, the correlation degrades, and then you have an information of the correlation, the two-time correlation of the intensity. That's really nice. That's fantastic. That works. But it opens some interesting possibilities. Let's just take a step here and see. When you see interference fringes, you're taking the average of the product of two fields with a delay time tau. That's kind of thing that's having a double slit interference in a Mach-Zehnder, in a microphone interferometer. Intensity correlation, you're comparing two intensities, or that's what you do in a Humphrey, Brown, and Twist, or you can say that's a second order, is a correlation in second order in intensity, or in fourth order of the field. Because if you open here, you have twice the field of being 1, twice the field of being 2. So we have these two kind of correlations that we're playing with. And now Glaubers enter with discussion, going quantum. So explore those correlation functions. So these functions G of n evolve in different detectors at position 1 to n. So going to that description of the state of the field, there will be the trace of these detectors, of these fields, but on this ordering. First, the annihilation operator, then the creation operator, written as this, okay? So that's the field. The E plus will be the frequency associated with this frequency E to minus I omega t. The conjugate will be E I omega t. And here, those are associated with the creation operator. These are associated with the annihilation operator. And those are the correlation functions that they are using with the quantum field. So we can see the interference for as this. The observable will be this term here. So this function will be the trace with the density operator. For Humphrey Brown twist, that's the operator that we are looking at. We can make the correlation now in the photon regime and look at the normalized second order correlation. What we're doing here, we're taking the correlation G2 for two different times, so we're correlating intensities, and normalizing it by the square of the intensity. G1 is the intensity of a single field. If they're even, so you're taking this correlation divided by the square of the intensity. So it's basically I1 times I2 averaged divided by I1 square. Here we are considering I1 equals to I2. And that's your G2. Now, if we're dealing with a single mode of the field, we can put the operators here to play. So this term here will be the sequence of operators, A dagger, A, and here will be A dagger, A square. Let's check out what this happens. We can use the commutation relation and reorder these. And we can see now that we have the variance of the number of photons appearing as n square minus average of n to the square, and rewrite this term in terms of your photon fluctuation minus your mean number divided by mean number square. Okay, this is the G2, or you can write this in terms of another parameter that's often described. That's the Q factor. That would be variance of n minus the average divided by n. Okay? This one, as you can see here, measures the deviation from a Poissonian distribution. Remember, for a Poissonian, these two terms will be equal. A super Poissonian distribution will give you a Q that is positive. A sub-Poissonian will give you a negative Q. As a consequence, you can see some examples. If you enter a thermal state, as we calculated before, you can go and make all the calculations using the P distribution. Since we have a normally ordered operators here, a function of the operators in a normal order, we can just evaluate the integration and see that this term comes with 2 average of n to the square, and when you see, you have a G2 equals to 2 for thermal light. So this coefficient for thermal light goes up to 2, thermal or chaotic light. And that's a signature of bunching. What's that saying? That the light that incides here, and then you detect, then you have a click here and a click here, it's quite common for you to have a coincidence here on the two. As if you had photons together that arrived here, each one of them has 50% of going through or being reflected. So, okay, sometimes you get the two here, other you have the two here, or sometimes you get one in one side, one in the other side. So detect a coincidence. You can work as well with, okay, that's basically the Q factor for thermal light. It will be n minus 1. And if you go to a coherent state, what you see here is that this term will be just alpha, modulus of alpha to the first. So your G2 will be equal to 1. Yeah.
Could you ask it to back again?
Mm-hmm.
And this is a thing that I also don't understand. Why, when Q is equal to 2, you explained it, but I didn't get it. Why, when Q is equal to 2, you are detecting 2 photons? I really couldn't see this, how this happens, because people of my group will use this all the time, and they say this all the time, but I cannot see this happening.
The point is that if you take the photons, so you have your photon flux here, and take slices of it, you get that Poissonian distribution is a P of n against n. That you goes, okay, I'll put some tail here. There'll be something like this. So you can have, let's say this is 0. In fact, it's a discrete function here, okay? Just making it continuous, considering that you have an intense field, but in fact, those are the probabilities. So you have a quite good probability of having 0 photons or 1 single photon. So you have a single photon, click here or here. So that's not contributing to your correlation. Or you can have 2 photons. Now with 2 photons, you have 4 possibilities. 2 coming out, 2 coming down, coming this way, or coming this way. So 50% of time, you have a coincidence. 50% of time, you don't have a coincidence. So this contribution here will be present in this case. If you go to the 3 or 4, so on and so forth, you have a different statistics coming out. And the statistics is given by this calculation using the P function.
Is that something more or less what happens in, for example, a Hongo-Mandel interferometer?
Not exactly. Hongo-Mandel will be an interesting effect, because in the Hongo-Mandel interferometer, we'll be using again the beam splitter, but you're not splitting the light any longer, but you'll be combining the photons on 2 ports.
Yeah, you're right.
And now there'll be a major difference that comes this way. But yes, that's basically the setup using Hong-Mandel interferometer, but then we are injecting something here.
In order to measure these correlations, you need to perform time-resolved experiments, right?
Exactly.
How do you do this with electronics?
Electronics, you just keep counting the clicks. The first detector, when it arrives, is the click opens a window of, say, some few nanoseconds, and you wait to see if you have the other click. If the other click doesn't come in this window, you don't count. If it comes, then you count a coincidence.
Thank you.
And so due to it measures so the probability to getting to clicks is
Not the probability. It measures.
because it can be less than you can calculate it and find less than 2, right? Or just 2?
Yeah, no, you can calculate and find less than 2, your G2, for instance, when you go to a coherent state. In that case of the coherent state, this term here gets to 1. Because you still have some bunching, you still have a probability. I made this, sorry. This is the Poissonian light. The thermal state will be something like this. It's a distribution. This is P of n for thermal. And this for coherent state. Coherent state. So this bunching, or the possibility of having a couple of events, or the level at which you have couples of events, will be higher for this situation, where you have this long tail. Then you have here, where you have a distribution that's concentrated. The dispersion here is bigger. Okay? So you go for the G2 in this case, you get G equals to 1. And now, if you get something that's a number state, and for a number state, you have 100% chances of having a given number of photons. Then it scales as this, 1 minus 1 over n. If you have just a single photon arriving, your G2 will be equal to 0. Because the photon arrives, it clicks here or clicks here. But the product will be necessarily 0. If you have 2 photons, okay, now it goes to 1/2. Because then it will be the effect that you can have either a click here given by 2 photons, or a click here given by 2 photons, or these 2 possibilities. Okay? That's what we call the effect of anti-bunching in your detection. That's the first signature that you have of quantumness in photo detection. Okay, it's a nice exercise to wonder what you have for a squeezed state or a squeezed vacuum. The first experiment on top of that was in 77. See, there's a sort of quite a delay from Glauber theory, 63, and then almost 15 years later to get it to an experiment. So basically, they make a coarse single photon source, a flux of sodium atoms coming here So you have the pumping of these atoms, excite them in the focus of a microscope that you collect as much light as they could and send it to a Humbury Brown and Twist experiment. And play with the delay line here, controlling what's the correlation that you have when you put a delay on this counting. And that's what they've got, a rate that increases and then goes down to a certain value. When they normalize it, that's what they have. It goes up and goes down. This will be the limit of a coherent state or completely random light, and this is the signature of sub-Poissonian light. So that's the typical observation that you look after whenever you claim, okay, I have a single photon source. You may be making the correlation and see if the G to 0 goes down to 0. As far as it can go down to 0, the better is your single photon source.
Professor?
Yep.
The picture on the right is the G2?
No, that's basically the counting rate. On the right, that's something related to G2. You can go a little bit up beyond 2, and then goes down close to 1. Okay, so we can see the measurement of intense field. But now, there's some point here. Let's consider now, instead of this weak photon flux, let's look for an intense photon flux. By an intense field, I mean that, okay, you can always write your field in terms of an average, a mean, plus a fluctuation. Okay, this will be a complex number. When you use this notation, you can rewrite your number operator as something that involves the average of your total intensity, a term involving the product of this mean with fluctuation and its conjugate, and twice the fluctuation, involving the field and its Hermitian conjugate. Often, when alpha is much bigger than the variance here, you can just discard this term and keeps the continuous part, an operator associated with the fluctuation, and discard these higher order terms. What you have here, repeated, is the observation of the amplitude, and that will be translating into one of the quadratures of the field. What you see here, A dagger to EI alpha plus A EI minus I, and not alpha, phi. What you see here is that quadrature operator that we have defined in the last class. E to I theta plus A dagger E to minus I theta. That's the quadrature operator, and you can see here that they are measuring, when you make the measurement of photocurrent here, now with an intense photon flux, you're measuring one quadrature of the field. It's nice, because remember what I've mentioned before, to get the construction of your state, you need to measure different quadratures. So when you measure intensity, you can do experiments at photon level, or going to continuous variable regime, you can measure quadratures of your field. What's the point here? The amplitude is related to measurement of number of photons, but you don't have the quadrature operator. You don't have Y of theta. That's be the anti-symmetric part here times I. That information is missing. But you need to convert then amplitude phase into amplitude fluctuation by making interference. You can add two waves and see how the combination of these two waves changes when you shift the phases. That's the idea behind the measurements making interference. And for doing that, we use, once again, a beam splitter. I would say that's one of the most powerful quantum machines in optics. You basically mix here two inputs, A and B, associated with fields, into C and D, that make this combination on the input. Okay, you can have different phases here, necessarily. They will combine here with a difference in sign, in the signal, in sign from plus to minus. And now, when you make the measurement of photocoherence on both sides, you have basically the number operator of A and B averaged plus the interference term. When you take these two and you add up, you just take the total photon flux on both parts. When you take the difference, you get only the interference term left. Now you can play a little bit. Let's say that here we are entering a strong field on port B. So strong that we would be treating it as a classical field. This classical field coming through this port, you'll be basically making a beat with this field coming through port A. So N minus will be giving you the quadrature operator, where you can tune your angle theta, multiplied by the mean field here. So that's the idea of homodyne detection. At the end of the day, it's an amplifier for the field fluctuations that are coming here. And it's a tunable amplifier because you can change the phase here, basically displacing this field, can add a glass plate and change the phase, or often you have a mirror and just move it back and forth, changing the time of light into this port. And now, from subtraction, you get the expression of this operator, and that's really nice. That's what you're going to see tomorrow. If you take the sum, you get the information of the photon flux here. You're saying that A is much smaller than this, so you can discard this term. If you block here the inputs, you have nothing entering this port. And there's something in that nothing. You have vacuum fluctuations. When you make the subtraction, the average gives 0, but the variance will be proportional to this field coming here. You're homodyning the vacuum, and that's give you the calibration of the standard quantum level. That's why the variance is. If you go to the calculations, often you see something that has a variance of this term using one quarter. Okay? Often, when people are doing with experiments, they'll put some multiplying factors in that combination of saying that A is equal to X plus I Y. Can have a factor of square root of 2 here or 2. Choose work in a situation where this variance will be normalized to 1. Because something is just the calibration that you have will be the vacuum level that you're measuring. What's curious here also is that when you take this variance, when you put that in the normal ordering, what you see here is the square, and the double dot here says that you're taking the normal ordering minus n to the square plus the mean value. Here, this normal ordering is giving you the classical variance. That will be the fluctuation of a field if you consider just a classical field that could eventually have a fluctuation down to 0. Quantically, the fluctuation is never 0, you always have a shot noise. That's what we'll see tomorrow. We will take an incoming field, but attenuators, and see that as you attenuate the light, this term comes down with the square of the attenuation, and this comes linearly with the attenuation. So the vacuum Raman line is a tool to make the calibration and produces a Poissonian statistics in the output that gives you this distribution equivalent to a coherent state. But remember, Poissonian distribution doesn't mean that you have a coherent state. You need to make the tomography of the state to say that. So whenever you make a measurement, you're taking a look at these variances, and there's an uncertainty relation involving a probability distribution for a given pair of quadratures. And when you make a measurement, you select an orientation, you shift this phase, you get a distribution, and then you can tomographically reconstruct this information, giving you the Wigner function. Questions?
I was going to ask you, how do you know to make a tomography?
You see, when you make a tomography, you see the different marginals. You change the phase to get distinct marginals, and so you have a probability distribution. And from the probability distribution, you make the inverse transform, this radon transform, to reconstruct the original
So this
Wigner
is the way that you see if a Poissonian distribution is equivalent to a coherent state. So you need to look for this distribution. You need to do this tomography and see, is that?
Exactly. I wouldn't say that is equivalent, but if it
Correlated.
corresponds
Ah,
to a
okay.
coherent state. Because the first thing that you see is Poissonian. Nice. It smells like coherent. But then I need to check the phase. Is it coherent? It may be, and maybe not. A good laser, like the ICTP-SAIFR laser, a very fancy, expensive one that you put on a tabletop, is pretty much coherent. Even a good laser, as a neodymium YAG, those that have come to our lab last week have seen on the teleport room that filtering cavity. Okay, the laser from the neodymium YAG, although precise, narrow line, expensive light that it has, it still has a good deal of phase noise that has to clean it up. Diode lasers, they can be Poissonian. They can be even sub-Poissonian. On the other hand, they have 40 dBs of excess noise in phase. 40. Okay, you are 4 orders of magnitude above. You need to tame that really well. You need a very long cavity. Probably, if you notice, the one in the microchip room, they have a cavity this big with a 4-path and high-quality mirrors to make it narrow and clean the noise coming out from the diode. It's tough. I mean, diodes are fantastic. They're absurdly cheap. On the other hand, comes to a drawback. There's no free lunch, okay? If you squeeze on one side, it gets crappy on the other side. On the other hand, diodes work just the other way around of the photodetector. If you send sub-Poissonian light into a photodetector, you get a sub-Poissonian current. If you take a diode laser working in a single mode, if you send a sub-Poissonian current, you get sub-Poissonian light. That's the advantage that comes with that drawback of having huge excess noise. A very short distribution on the pump of your laser gives you a short distribution in the output, on the photon counting in the output of that diode laser. Okay? Now, the last part of the class, you're already late. I'll take 10 minutes more, because I need to finish this, to tell you something that was missing along this of this description. See the variance, we take the average, pretty nice, everything is perfect, but let's say that you have this measurement and you see all this noise coming out here. I mean, is there any difference in them? Except for the color of the dots? Meh, noisy. Let's say that corresponds this as something like this, okay? You're measuring, say, oh, yeah, should there be some squeezing here? That's the tomography. Often, I'll be using P for the amplitude associated quadrature, Q for the phase associated quadrature. So you see that if you have a phase fluctuation, that be producing a contribution here, amplitude fluctuation will be like this, that can translate into X and Y coordinates. But there's something hidden here. If I take the Fourier transform, that's produced data, that I added a sinusoidal into the noise, and you can see here a line. The black dots has a frequency here, the red dots have another frequency contribution here. Often, when you make a measurement, you're not taking just this single, but have all sort of noisy contribution from the 60 hertz of the outlet to the noise of the air conditioning to all the antennas that you have around contaminating your electronics. So, when you take a time measurement, you're taking all that crap with you. Either you get really a dramatically shielded room, and then, okay, you better do your experiment the other way, or you make an electronic filtering. You go for a region of silence. You can see your operator, A of t, as the Fourier transform of an operator A of omega, where omega is a frequency that's associated to the sideband of your central carrier. How do you mean sideband? Okay, you're going to that in a few. Just saying that when you make this measurement, you're making at the end of the day, that's the equipment that we're going to play tomorrow. You have this photocurrent. You make the mixture with an oscillator, pass through a low-pass filter. Sorry for the Portuguese. This is a low-pass filter. You measure the peak, and you present that on the screen. So what you're measuring here, in fact, is not this guy here. It's the average of this guy here. We're measuring the Fourier transform of the two-time correlation. We're measuring the Fourier transform of the product of the values read by these two bars. And that's something that we do 99% of the time when you deal with variable domain, with continuous variable domains, with photodetectors. In fact, that's what the guys in LIGO do. So the folks in LIGO, when they make the measurement, they are observing this at different values of omega. And afterwards, they clean up the noise and get the two-time correlation. What's that two-time correlation? Why I said sidebands. Let's begin with a classical field at frequency omega naught. A coherent state is not a wave with a well-defined amplitude, but has some fluctuations. Those fluctuations come from the contributions of vacuum fluctuations over all the other sidebands, all the frequencies around. Here I'm saying 300 terahertz. Here I'm on the range of gigahertz. So I'm 5 orders of magnitude down, or far lower. When I say that I have a squeezed state, often I'm measuring a specific pair of sidebands, and I see that the amplitude, for instance, the noise here is reduced because these two sidebands are correlated. Why do I say that? The field can be seen as a monochromatic wave plus a fluctuation. If you have amplitude fluctuation, if there's this fluctuation here modulating the amplitude as this, what you get is a pair of sidebands in frequencies omega plus major omega and omega minus major omega. In the detection, when you look at photocurrent, at this current capital omega, you're seeing the beat of these two sidebands with the central carrier. And that's what you're really measuring in the output of the spectrum analyzer.
Marcelo, this omega 0 is the frequency of the sign.
It is the
Signal?
frequency of the wave that's coming into your detector.
Okay, so we have this omega 0 minus this big omega and plus big omega, okay. This is, you have exactly 2 points, one at the right, other at the left, or some kind of distribution?
A coherent light, a perfectly coherent light would be a delta function here and vacuum noise all over. In fact, it's not perfect. It will be something more like a Lorentzian. And Lorentzian is quite sad because it has the wings, they drop badly. Or it can be a Gaussian, depending on the laser that you have. Diodes will look much like that Lorentzian, so that's why they give that, all that noise. A TIE-SAIFR will look more like a Gaussian. That's why it's nicely narrow and silent. And what you have here is different states of light at specifically all these frequencies. So when you make a measurement, often you're not measuring specific, just one frequency. You're measuring the contribution of all of them. That intensity that you see, you have a mean, that is this contribution squared, plus a fluctuation. That fluctuation in time corresponds to a spectral domain that involves the bits of the sidebands with the central carrier.
Okay, so so you don't see a peak there and a peak there. It's just like a bit of beating.
Yeah, this is really where the main part of the energy is. But when you look at the fluctuations, you see the contribution of those sidebands multiplied by the central carrier.
Okay.
Okay, if you're making the homodyning, you're entering this strong field to that port B, and this flat is coming to port A. So what you see is this fluctuation beating with the central carrier in port B. That's the idea of the homodyning when you make the Fourier transform. So you get some excess noise here, but you just discard the information here and here. Look at a frequency where you're silent at the beginning. And this fluctuation here can be translated into an amplitude or phase fluctuation. If your fluctuation is here in the argument on the complex part of this amplitude alpha, so it will be a contribution of the sidebands with a pi over 2 phase. That should be in the distribution in a few. I passed the slides for the guy. So that's I just brought it into attention. So that's what you do when you make homodyning. You're taking this carrier to run port and bits with all the frequencies entering through the other port. But also, whenever you have a strong field coming, you can make a self-homodyning. You can tell apart the central carrier from the sidebands using a cavity. When you have light reflection of a cavity, the reflected light here acquires a phase that goes from 0 to 2 pi as you detune it. In fact, in the reflection, your field is doing something like this. From version to version of PowerPoint, the center of this rotation displaces randomly. This is a nice article that was made by one of our students, Alessandro Villar, that he used it to make the measurement, a full measurement of a strong field. The problem of a strong field is that you cannot make the beat with the local oscillator, because then the strong field making the measurement of the noise that's in the local oscillator, that becomes disastrous. But you can use the carrier to tell apart that's the field that you have, involving the contribution of two sidebands, that's what you want to measure, and the output reflected off the cavity will have a term of phase involving the central carrier and the phase of the two sidebands. Now, when you scan the cavity over the state, you have the carrier and sidebands, you first shift the phase of the lower part, shift the phase of the carrier, and then shift the phase of the upper one, and you change the projection along the mean value. Now you don't need the local oscillator, because the beam itself acts as its own local oscillator for measuring the noise on those sidebands. That's a technique that we call self-homodynic or cavity detection. Now if you put a cavity in front of your detector, reflecting the light into your detector, now your detector becomes a phase-sensitive equipment. In fact, it's something a little bit more blurred than that, but as far as you get this width is smaller than this separation, bigger than square root of 2 of this width, you can make the full rotation and measure both amplitude and phase quadratures.
And how do you change this? Is moving the mirrors of the cavity?
Exactly. You have a piezo actuator, and you can displace that by some few wavelengths. Here will be a fraction of a wavelength that you're displacing, just by applying a voltage. The other microphone? Okay.
So I might be wrong, but in this kind of self-homodyning, it is still necessary to have like a laser with very low phase noise?
Yes, to start your experiment. So how are you processing the light that is giving you this exquisite state?
Oh yeah, you're processing
You're starting with your driving laser that's making the whole setup move. So often you want to start with as low noise as possible.
Okay, okay.
So that will be the subject of the class on this afternoon. We're going to see how you enter the phase and the laser, and then you have the machine processing the state of light to give you the output.
Perfect.
Okay? I said 10 minutes. I made that. So, questions? No questions. I'll see you in the afternoon. We're going now to process the light. Now we have seen how to quantize it. We have seen how to describe. We have seen how to measure. We will be seeing now how to process the light. See you later.